Hey everyone, welcome back. This is going to be a really quick section. I just want to take what we just learned, talking about big O notation, time and space complexity, analyzing code performance, take that content and apply it to the stuff we already know. So before we get to the advanced algorithms and sorting and crazy data structures, let's just talk about what we get for free, the basics in JavaScript. So things like arrays and objects, built-in methods, loops. How do they perform? What are the easy things, the fast things we can do to an array? What's a method that might be slower than you would expect? That's what we're going to talk about. And it's going to be really quick. Again, I'm not going to teach these things from scratch. I'm not showing how an array works or what it is. We're just going to talk about how it performs. So first, our objectives. Understand how objects and arrays work through the lens of big O. So various operations. Is there a fast way to insert to an array? Is there a slow way? That sort of thing. Explain why adding elements to the beginning of an array is costly. Gave it away. And we'll talk about why that is and how it works, and if there are alternatives, if there's a better way of inserting. And then we'll compare and contrast the runtimes for arrays and objects, but also their built-in methods. There's a lot of these methods we get for free, like the built-in JavaScript sort for an array, for each, object.keys, object.hasOwnProperty, all that stuff we're going to discuss. But it's going to be quick, and this isn't, I should set out and say, this isn't something you need to memorize. It's not something that, you need to refer to these slides. I just want to give you a chance to take what we've learned about Big O and apply it to something tangible before we dive into these crazier algorithms. All right, so let's start. First, we're going to discuss objects. It will be nice and quick, so don't go anywhere. I'll see you in the next video. All right, welcome back. So let's begin by talking about objects, talking about them through the lens of Big O and performance. Hopefully you're familiar with them. If not, I don't have time right now to teach them, but I may or may not have some courses on them. So they are unordered data structures, and everything is stored in key value pairs. For example, like this object literal, I'm storing in a variable called instructor. We've got 3 key value pairs. All right, so objects work well when you don't need order, of course, and also when you want fast access and insertion and removal. So no order, but everything else, almost everything else, is very quick. And when we say quick, I'm talking about constant time for insertion, removal, and accessing data. So objects are very fast. I mean, that's the fastest we can go, constant time. We'll come back to searching in a moment. If we hop over here, here's the same exact object. We later in the course have a section called hash maps, where we actually learn a data structure that explains how objects work behind the scenes, how things are actually stored. So what happens when we say instructor should have first name set to Kelly, what does JavaScript actually do? A computer can't necessarily just access a place in memory called first name. So there's some additional steps involved along the way. There's something called hashing. We talk about it later in the course. But all that you need to know is that JavaScript is able to add something into an object, store a new piece of information in constant time. It's also able to retrieve something in constant time, and you could also update something in constant time, which is really the same as retrieving it. You're just changing it. Same with removal. So it's quick, it's fast for all the basic operations. There is no order, so there's no beginning of the object, there's no end. So it doesn't matter where you insert because there is no where. That's a bad way of putting it, but you can't insert at the beginning or in the middle or the end of the object. There's no repercussions. You just add in using a key. All right, so insertion, removal, and access are all constant time, very quick. If you want to learn more, remember there's a section on hash tables and hash maps where we go into that, and you'll hopefully understand how it is constant time. Searching, however, is O of n. It's linear time. And when we say searching, it doesn't mean looking for a key, for example, first name, because as we've already seen, accessing information with a key is constant time. What I'm talking about is checking to see if a given piece of information is in a value somewhere. If it's on this side of the colon, we have no easy way of doing that. We would potentially have to check every single item, every property. So that's what this little black box is signifying, or green box, I guess. If we wanted to know, is true stored in our object somewhere, we'd have to check. First name, what's your value? And then we look at it, it's Kelly. All right, that's not it. Is instructor, what's your value? True. All right, so there is true in here. But potentially, as the number of properties in there grows, as n grows, so does the amount of time it takes to do that. So now let's go on to some of the methods that objects come with. Things like keys, values, and entries, those three are all O of n. So if we hop over back to Chrome and we take a look at keys, so it's object.keys, and then we pass in the object. So if we do it for instructor, we get this array with the keys. This is O of n time, because as the number of items in there grows, we're going to have to visit every single thing once and add it to this array. We're not going to, but the source is going to do that, the code. Same thing with values. Hopefully that makes sense. If we have 100 elements or 100 properties in our object, there's 100 things, 100 operations we need to do. There's usually more, but it runs roughly in line with n. It might be 2n, it might be 50n, but that still simplifies to O of n. And then that also is the same for entries, right? And technically entries is a little more work, potentially having to compile the key and the value, but it all just simplifies to O of n at the end of the day. Remember. Okay, so lastly, we've got has own property. And has own property is a little different. We pass in a property like first name, and it just tells us it has first name, or it doesn't have first name. And this is constant time. And hopefully that makes sense why it's constant time. If we're able to access information in constant time, if we have the key first name, we want the value. We should also be able to check if a key exists in pretty much the exact same time. So in summation, objects are really quick for pretty much everything. However, there's no order. And as we'll see coming up with arrays can be pretty fast for a lot of things, but the order also can slow them down depending on what we're doing. So objects are basic. They work very well in a lot of situations. Key value pairs, all the main operations, inserting, accessing, updating, removing, all constant time. Searching is pretty rare, but it is O of n. It grows as n grows. It's linear. And then the methods like keys and values and entries, where we're creating an array based off of the data inside the object. Well, as the object grows, so does the number of operations, the amount of time it takes to compile those. So those are O of n. Okay, so next, arrays. A little more interesting because there's some variation. There's some nuance to it that's coming up. All right, welcome back. This will be really quick. I just want to touch on some of the built-in array methods. There are many of them, and I want to stress that you do not need to know or memorize any of this information, but hopefully it makes sense as to how we arrive at the numbers when we're talking about big O notation. So again, I have a little emoji. You don't need to know all of this. But let's take a look. The first four we've already discussed, maybe not by name, but push and pop are constant time, adding and removing data to the end of the array of any array, whether it's one item or 10,000 or a million items, is constant time. It's easy. There's no re-indexing involved. We just put it at the end and give it a spot. That's basically it. Shifting and unshift, on the other hand, are a little more troublesome because we potentially have to reindex, well, not potentially, we have to reindex every element in the array if you're adding to the beginning or removing from the beginning. So as the number of elements grows to 10,000 or a million, then the number of things we have to reindex grows in proportion with that. So it's O of n, it's linear time. So those four, adding and removing, we've discussed. I'm trying to highlight the top four. Well, no. Okay, well, that's the best I can do. So next up, we've got this little chunk of concat, slice, and splice. So all of these are O of n, linear time. And there can be some confusion. Something like concat takes multiple arrays and merges them together. And when we say O of n, you might think that that just implies, one array of n elements, and we're acting on that one array. What happens when there's two? Technically, you could argue that it should be, O of n plus m, where m would be the size of the second array. But O of n is fine. It's basically just expressing the fact that as these arrays grow that you're merging, so is the time that it's going to take. And it grows in proportion with the size, the total size of the new array at the end. What else did we have? Slice and splice. So slice is going to return a copy of part of an array, or the entire thing if you want it to. So O of n in this case refers to the fact that if we're trying to copy 10 elements versus 1,000 elements from an array, the amount of time it takes grows in proportion with that size, how large of a copy or how many elements we're trying to copy. So that's O of n. And then lastly, what we have? Splice. Where are you, splice? There you go. And splice is going to remove and add new elements. And splice is a little different because it's quite versatile. So we can insert at the beginning of an array, We could also insert at the very end of an array. We can replace given elements, but in general, it's O of n. If we're inserting in the middle of the array, we just simplify that to O of n. Remember, that does mean shifting and re-indexing everything that comes after it. So even if it's only in the middle, we would still say it's O of n, even if it's O of n divided by 2. We just don't care about that. So in general, a lot of things working with arrays are O of n. You may have noticed this one down here, sort. Array.sort O of n log n. So we're not going to talk about how this is derived, where the log comes in, where the n comes in, why they're multiplied. We spend a lot of time talking about sorting algorithms, and there are many of them out there. We talk about 6 or 7. I think it's 7, but I'm not positive. We talk about a lot of them. And some of them we talk about have a time complexity of O n log n. So we'll explain how we get there. But just know that the time it takes to sort an array is larger than just O of n. We have to make comparisons. We have to move things around. It's not enough just to look at every element once, and that's not enough just to sort it. It's a little more, sometimes a lot more complicated. So just keep that in mind. Again, we're not explaining how we get this, what the math is just yet, but it will make sense in due time, I promise, if you make it to the sorting sections. So sort is the slowest thing on here. And then things like map, filter, reduce, for each are all O of n. Those are looping over each element or doing something with each element, tallying it, doing a Boolean test, or just printing them out, or whatever we're doing. It just involves acting on each element or with each element. So as the size of the array grows, so does the amount of time it takes, O of n. So you can see almost everything that we could do with an array, all the built-in methods, not all of them, but all the ones listed here are O of n. Sorting takes longer. And then push and pop are super fast, just like with basic accessing using an index, super fast as well, constant time, and they're much faster than adding and removing from the beginning, as we've talked about. Okay, so that's a lot. And remember, you do not need to know all of this. Really, the main takeaways here between objects and arrays: 1, objects are fast at pretty much everything, but there's no order. 2, arrays are great when you need an order, but still be mindful that it's better if you can do it to add and remove from the end and avoid adding and removing from the beginning, because that starts this cascade effect, hence the term shift and unshift, and everything has to be re-indexed. And the same goes to adding and removing from the middle. You start another cascade, a little tidal wave, and things have to be re-indexed after whatever you added or removed. All right, so hopefully that makes sense, how we get to these numbers, what the values mean. If not, we'll be spending a lot more time talking about big O as we go. And this is really a primer for later on when we get to things like sorting, or when we talk about linked lists and how they're also an ordered data structure, but we can add and remove from the beginning and there's no problem. It's constant time. So how does that work? So we'll get there. That's coming up. That's all I have to say about arrays and objects. We're done for now. All right, welcome back. Let's talk about arrays through the lens of big O, performance, and how do they compare to objects. Quick side note, if you've never seen arrays or you're not familiar with them, definitely go learn about them first. I'm not teaching them here. We're just talking about them and how they perform. All right, so the big selling point of arrays, of course, is that they are ordered. There is an intrinsic ordering to the data, unlike an object where things just float around in a gelatinous mass. And that's often very useful if we need order, but it can come at a cost for some of the operations. Anyway, here are 2 different arrays. Of course, we can store whatever we want in there, different types of data, mix it up. And each element has an index, a numeric value that corresponds to it. So this is the 0th item, the first item, the second item. And in general, arrays, you use them when you need order. If you don't need order, then you probably don't want to use an array. If you're just trying to store random data together, you could still use an array, but if you're really trying to optimize for performance, there are other options. And even if you do need order, we're going to see some other structures coming up, like a singly linked list and a doubly linked list, that still encode order. It's a list structure where each element is in a particular spot and they're all connected in an order, but they sometimes can perform better than arrays, depending on what you need. So arrays are not the only ordered data structure on Earth. They're just the only one that we get for free in JavaScript. Anyways, linked lists come later. So when you need an order, you can use an array, of course. But often that can come at a cost, depending on what you're trying to do, especially around insertion and removal. It can complicate things. So accessing data in an array is always very quick. So you can see here, access is O of 1, just the exact same as we talked about with an object. When I say access, what I mean is if we have this array with 3 items called names, if I ask for names of 0, or maybe that one's too easy because it's the first one. Let's say I ask for names of 2. It's constant time to give me Andrea. So a misconception that I've seen a lot of students have, when you have a 10,000 element array and you ask for the 9,000th element, let's say, JavaScript isn't going through every single element and counting all the way up to 9,000 and accessing every element and then getting to the one you need and giving it to you. You can think of there's a direct shortcut to each element. If you have a number, if you have an index, and the array goes that far, of course, that's the one condition, it's a valid index, you can jump immediately to the data. So it doesn't matter how long the array is. It doesn't matter if you're looking at the last item, the middle item, or the first item. It's constant time. Okay, so now that that's out of the way, let's talk about insertion and removal. So it really depends on where we're inserting. Let's start with insertion. And it has to do with this order, as I've mentioned. Each element has an index that corresponds to it. And if I want to add something in, let's say I want to add in the name Raj. Well, if I add it to the very end, like right here, by pushing onto this array, that is constant time. It's O of 1. And that's because there's nothing difficult about that. We can add to the end of the array and we give it a new index. It's sort of like adding into an object. It's constant time. It's super simple. It doesn't require much work. The problem comes when we try and insert at the beginning of an array. And the reason for that has to do with these indices. If I tried to insert Raj here, you can already kind of see what happens. Our indices are totally messed up. Michael is no longer element 0. Melissa is not element 1. Andrea is not element 2. So we have to re-index every single element in the array. And this is simple for a 4-element array. But if we're talking about thousands and thousands of elements, re-indexing every single one is not a trivial task. So if we're inserting at the beginning of an array, we're talking about O of n time, because we have to do something once, roughly once, for every single element. Now that doesn't mean that it's exactly one operation for each element. Remember, O of n, it could be O of 10n, O of 2n, O of 0.5n. It's just that the amount of time it takes roughly grows in proportion with the size of the array, n. All right, so inserting at the beginning is problematic. The same goes for removing from the beginning. So if we do have Raj at the beginning, let's say this is our setup now. Oh, this is so annoying, having to type all of this like this. If we remove Raj like this, everything's wrong, right? We have to reindex again, just the other direction. We need to set Michael, its index, or his index is 1. Melissa goes down, 0. Melissa goes to 1. Andrea goes to 2. So you can see how this becomes difficult. Adding and removing from the beginning of an array is best to avoid if you can. But often it's meaningful to add to the beginning of an array. If you're trying to put something at the beginning of an order, for example, you may need to, so I'm not saying you should avoid it at all costs. It's just good to be aware that it's not as efficient as adding and removing at the end. So push and pop, always faster than shift and unshift. Unless, of course, it's an empty array, in which case adding to the beginning or end is the same thing. All right, so we talked about insertion and removal. It depends on where we're inserting. Always inserting, removing from the beginning is worse than adding to the end and removing from the end. Accessing is fast, no matter where. If we're talking about 10,000 elements, accessing the middle element is just as fast as accessing the second element. And then searching, the fastest we can do is O of n. We'll discuss this in the searching section. We'll write our own basic JavaScript search. If we're talking about an unsorted array where there's no order to the data, if I wanted to know, if I had, let's say, another 10,000 names in here, and I wanted to know if Robbie was in there, we have to check potentially every single element. So as the number of items grows in that array, so does the time potentially that it takes to find that item. So search grows, O of n, it's linear. And we spent a lot more time talking about search and potential optimizations you can make, specifically when your data is sorted, but that comes up later. All right, so next we'll talk about some built-in array methods and their performance, and then we're pretty much done.